Electricity price is definitely a really important piece of the puzzle, but I think right now you really don't have the technical solutions in the hydrogen industry, right? You have like a product that can solve one problem, but not the other. And so the technology, as well as hydrogen infrastructure in general, really needs to improve.
Greetings, Earthlings, and welcome back to Earthlings 2.0, the show where we imagine how we could be better versions of ourselves and build a collective future we actually want to live in. Today, the growth of renewable energy is transforming how we generate power, but it also is creating new challenges for us to overcome, especially when it comes to storing energy and grid resilience, because we all know wind and solar are abundant when they're available. So we want to make sure we can manage their intermittency, and that requires smarter solutions to keep the electricity flowing. That's where hydrogen is coming in, both as an energy carrier and as a powerful tool for decarbonization, especially if it's green. However, there are a variety of electrolyzer solutions out there, and they each suffer from either hidden costs or constraints around the supply chain or reliability. And that's where our guest's simple hybrid electrolyzer innovation comes in. But before we beam our guest up to our proverbial spaceship, I'm your host, Lisa Ann Pinkerton. I'm the founder of the award-winning PR firm Technica Communications and the founder of Women in Clean Tech and Sustainability. Before building those organizations, I was an award-winning environmental science, tech, and healthcare reporter for NPR and PBS. And I want to give all of you a big thank you for being here today. You could be doing anything with this time, and you're listening to the Earthlings 2.0 show, and I really appreciate that. Thank you. It's our joy to bring you these stories every week, and we're excited that you enjoy them as well. If you want to get more involved, you can subscribe to our Substack newsletter. That link is in the show notes. We'll give you a monthly digest. We're not going to spam you, and that's just going to keep you up to date on what's going on the show. You can also take our listener survey that is also in the show notes. Click on that link and tell us what you think of the show. It'll take you 5 minutes, and it's going to give us a deeper understanding of who you are as an audience, and then we can better tailor our show for you. And I want to thank everybody who's been contributing to the show, either financially or by sharing the show with a friend, especially sharing the show when you're talking about podcasts, you're referencing a piece of information that you learned from the show. That is one of the most effective ways you can help support the show and help us to grow. So thank you very much for your support. And thank you to Resource Labs for having us on the network. On today's Tech Spotlight, we're featuring Power to Hydrogen. They are a company pioneering hybrid electrolysis technology. And if you haven't heard of such a thing, don't worry, you are not alone. Hydrogen electrolyzers are a pretty unique innovation, which is exactly why we wanted to have our guest onto our show. His name is Alex Zorniger, and he is the Chief Commercial Officer of Power to Hydrogen. And this is a company that is innovating with hydrogen technology by lowering the costs and integrating renewable energy and using earth abundant materials. So we have a lot to talk about on the show. So we're going to catch up with Alex. He's calling in from Columbus, Ohio. Alex, welcome to the show.
Thanks for having us, Lisa Ann. We appreciate it.
Oh, you're welcome. I'm really excited to dive into this because, like I said, it is really unique. And whenever I see something so unique, I want to learn more about it. So let's get started on what do you mean by a simple hydrogen electrolyzer?
Yeah, so at the very basis, so an electrolyzer applies electricity to water to split it into hydrogen and oxygen. So you don't have any CO2 emissions, you're just getting hydrogen with oxygen emissions, which are not harmful to the planet. So if you were to buy an electrolyzer today, you really could choose from two different options. One is a kind of a low performance electrolyzer. It uses low cost materials, but you can't use variable electricity, so you can't use wind and solar. So you have to tie this electrolyzer into the electricity grid. And if you have carbon intense electricity from natural gas or coal, you're not really going to end up reducing the emissions even though you're using electricity to make the hydrogen. There's another type of electrolyzer where it's called a PEM electrolyzer, and I'll explain a little bit more about that later. But so this technology is pretty high performance. It can tie directly into wind and solar to make the hydrogen, but it needs really expensive materials like platinum, iridium, and titanium. So these are very expensive machines, which contribute to the higher cost. And so our technology is looking to remove all those expensive materials, use things like nickel, stainless steel, and iron, while still delivering that high performance. So you can have a low cost electrolyzer that can make it from renewable energy.
Are these challenges around the high costs and the rare materials that are required, is this one of the reasons it seems like the concept of green hydrogen has been slow to evolve as a solution compared to solar and wind?
Yeah, I would say so. So, electricity price is definitely a really important piece of the puzzle. But I think right now you really don't have the technical solutions in the hydrogen industry, right? You have a product that can solve one problem, but not the other. And so the technology, as well as hydrogen infrastructure in general, really needs to improve. And so we're tackling the problem for the hydrogen production, but also, we can talk about this later, but we're also working with organizations like NASA to go to very high pressure with the hydrogen, because typically when you need to move hydrogen, you also need to go to high pressure and use compressors and things like that. So we're trying to eliminate that. But I would say it's definitely the technology as far as the hydrogen production, but as well as just the available infrastructure at play.
Okay, well, walk us through what AEM means and give us a little bit more of a deeper dive into how your electrolyzer works.
Yeah, so I mentioned the term PEM. So it stands for proton exchange membrane. So essentially, the earliest type of electrolyzers that were invented nearly a century ago. They're called alkaline electrolyzers. And so there's no membrane in this electrolyzer. So when electricity is really varying as far as wind and solar and going up and down, the hydrogen and the oxygen can actually start to mix because there's no membrane separating them. And so that's one of the challenges why they struggle to use wind and solar. So these PEM electrolyzers use a proton exchange membrane. So it's a membrane in the middle. And with the materials that make up that proton exchange membrane, essentially the electrolyzer is in a very acidic environment. And that's the reason why it needs to use really expensive metals so they don't dissolve in the system. And so really it's a materials challenge. So what we're doing is we're using membranes. So our membrane is called an AEM. It's actually an anion exchange membrane. So it's just a different chemistry. It's still a membrane, but it's a different chemistry. And so it's more on the alkaline side. So we don't have to use really rare things like platinum and iridium. We can use things like nickel and iron instead. So that's kind of that key innovation is you still need a membrane to be able to handle the variable electricity, but you need to make sure you're not creating a really acidic environment that's going to make sure or ensure that you use very expensive materials.
So, what is it about that acidic environment that requires the more expensive materials?
It's like if you've ever done that scientific experiment where you put like metal in a can or like a bucket of Coke, right? It just dissolves it.
I like the penny when it takes the tarnish off.
That's
Yeah.
exactly it. And so that acidic environment's really challenging and forces you to use rare and exotic things. So it's actually been interesting. While the alkaline environment, so moving away from acidic, the alkaline environment is easier on the metals. The reason the technology that we use, so AEM or hybrid electrolyzers, hasn't made it really to the commercial scale yet is because it's actually much harder on any of the polymers in the system. So any of like the plastic materials that you use in the system, it's a little bit more corrosive there. And so that's where there's needed to be a lot of intellectual property and a lot of innovation to solve those challenges. You can use lower cost materials, but you still need to solve some of the materials challenges on the membrane and the polymers and things like that. And so we've solved those, and that's why we're scaling up now.
Yeah, I was talking to somebody else about electrolyzers a while back, and it just seemed like this is not a scientific assessment by any stretch of the imagination, but it seemed like the electrolyzers were very leaky, and half of the challenge is like trying to contain all of these chemicals, and that's why things were corroding.
That's a really fair point. I've actually thought about this a lot. One of the interesting things and the difference between electrolyzers and batteries is batteries are kind of closed loop. You charge the battery, you discharge the battery, you charge the battery. There's some of the similar materials used, but because it's closed loop, you have less variables. With an electrolyzer, we are always taking water in and is coming out of our system as hydrogen and oxygen. So you are always exposing potentially new contaminants into the system. So it's kind of like an open loop system. So that's one of the reasons that makes this a little bit more challenging from a quality perspective than a closed loop system like a battery. So your point to they can be leaky or challenges like that, that's certainly a valid comment.
Okay, and like oxygen's corrosive, right? So anytime you've got oxygen in a system, you have to really work against the oxygenation of whatever that element comes in contact with. And then hydrogen is also really light. Also, unscientific term. It seems very small and it can get into little crevices and things.
No, but I mean, maybe not a scientific term, but just a very accurate term, right? I mean, it's at the top of the periodic table, so it is small. So it is going to leak more than other things. One of the nice things about, the origin of our technology is we first won a grant from NASA to develop it. And so NASA is one of the, global leaders. They've been working with pressurized hydrogen and oxygen for a very long time. So they've been very helpful in that demonstration or the development of the technology. I think they're the global leaders in that.
I can see how that's going to be useful in space. Hydrogen technology, perfecting that for use in space is really critical.
We are certainly most focused on decarbonizing things in our globe, but there are some really cool applications for hydrogen in space. So one of the projects that we first worked on is essentially they're taking ice that they found on the moon, melting it, and then using an electrolyzer to split it into hydrogen and oxygen to make rocket fuel on the moon. So I mean that's a wild project, very cool. One thing they can do is they can store the energy by splitting that ice. And one of the things we've learned is that it costs $1 billion per ton to ship things to the moon. So if you're going to ship batteries to the moon, it's very expensive. But if you can just ship something that makes the energy storage basically from the water or the ice, it can be much cheaper. Now, these are very pie in the sky. I mean, we do have the Artemis mission that's hopefully launching this decade, but very fun things to talk about as well.
Yeah, I like how you say hopefully launching this decade. Like lots of
Yeah,
caveats in there.
I've seen some desires for large budget cuts recently, so hopefully that
Yeah.
doesn't affect things.
Yeah, I hear you. Let's get back to other applications. What are you targeting right now in terms of your markets and your commercialization?
Yes, a very good question. I'll go back to one of the things you said about hydrogen being potentially leaky. So, it's great to find opportunities where you have, renewable energy to make hydrogen and you have an existing hydrogen user today. So kind of all of that's localized. So you can do this potentially in Texas, where there's lots of the two largest uses of hydrogen today are petroleum refining and ammonia production. So you've got nice renewables in Texas. You also have lots of hydrogen use that's currently coming from natural gas. So there's a really good opportunity to decarbonize those opportunities with local production. But when you think past that, as far as what can we do that's also valuable with, potentially, there's a lot of renewable energy that is not being deployed today because there's either grid constraints or there's so much renewable energy on the grid that sometimes we're getting negative prices. And so there's an opportunity to make really valuable products with those. It's just, if there's not a local use, we need to think about how are we getting this product to the end user. And so that's why we're seeing a lot of demand in the industry for, I'll call them hydrogen derivatives. So things that you're going to make with hydrogen, that's actually typically a liquid fuel. So it's either ammonia, so you're basically taking nitrogen from the atmosphere and adding it to hydrogen for ammonia, very easily shipped. There's a supply chain for that. A lot of talk in sustainable aviation fuels about e-fuels. So essentially you're making it a chemically identical product to jet kerosene out of hydrogen and captured CO2. Also potential for just remaking LNG out of captured CO2 and hydrogen. So that's what we're seeing a lot is when you're not thinking about local use, it actually is going to be valuable to use the existing transportation infrastructure that we currently have in making hydrogen derivatives rather than thinking about maybe globally transporting gaseous hydrogen. And liquid hydrogen is typically very difficult too because it's so cold. So we're seeing a lot of demand for making it into ammonia and making it into e-fuels and making it into electric natural gas.
Yeah, that's smart because as I've heard we interviewed Val Metcalf over at Zero Avia. We'll link that show in the show notes. They're doing a hydrogen electric powertrain technology, and one of the things he enlightened me on was this idea that it's really the transportation cost is where a lot of the expense of hydrogen energy comes from. Their vision is to also do on-site hydrogen production for the airplanes. And so I like what you said about using existing transportation and transport infrastructure for these. I've also heard people say, oh, well, we can just use existing pipelines for hydrogen, but then getting back to the idea of it being leaky or like being really small and can make its way out of things. People have argued that that wouldn't actually be very viable.
Yeah, my opinion on that, I think it's actually a good idea. Number one, there are rules right now for what actually the definition of natural gas is. And so natural gas can have hydrogen in it and meet pipeline regulations. So there's potential to blend hydrogen into natural gas pipelines. There's also some cool technology that they're talking about where they're retrofitting pipelines. But the problem is, it's like a very what's the right term? It's a very fragmented legal landscape. And so, like, yeah, technically we can do this, but oftentimes pipelines are going in between states. Who owns the pipeline? Like, technically, I like it, but it's going to be very hard to implement without like a lot of work on the regulatory side. And so many of these things, at least in the US, are states' rights focused. So it's just like a very hard problem to solve on the regulatory side, too. And finding pipeline owners that are willing to consistently let you, bring hydrogen into that pipeline. There may be one, but all these pipelines are interconnected, so it's a logistical challenge from that side as well. So it's not so easy even if you can solve the technical challenges.
But so just for clarification, when you're talking about blending natural gas and hydrogen, is the theory that put the hydrogen into the natural gas pipeline with the natural gas, and then on the other end you separate them out to use them separately?
There's technology to do that, certainly. I think the problem with that all is like the consistency of it. Like, what ratios are you getting? Can you depend on the hydrogen being there if you have a hydrogen separator at the other side? So yes, these are the challenges that make it like maybe we'll do this in 2050, but it's not something that I think is going to be, the solution that we're looking at today.
Well, and we talked a little bit about how using these earth abundant materials is one of the ways that you're going to reduce the costs of your technology compared to others. So, can we get a little bit more into that? Like, how much of a reduction in cost are you expecting?
So when you talk about electrolyzers, there's a term, the stack, which if you think about a car, it's really the engine of the car. So the stack is where a lot of the precious metals are used. And then that engine of the car, we would call like the balance of plant. So that's all the sensors and pumps to circulate the fluid and things like that. So on the stack side, so we're reducing the cost with these no precious metals by about 65%. So it's a 2/3 cost reduction. It's really significant. But you still do have to think about that whole ecosystem as far as the stack, the balance of plant, this whole site works that you're doing. But so, cutting out those expensive materials are a really key part of it. But I mentioned this a little bit earlier on as well. So it's not just the stack that we're cutting costs out. So when we've been working with NASA in the past, going to very high pressures without the need for a hydrogen compressor is really valuable because sometimes the compressors is as expensive as the electrolyzer. We've been looking at some refueling station projects and the compressors are extremely expensive. You talked about hydrogen being a leaky molecule. That's one of the reasons that these hydrogen compressors are expensive. It's hard to compress it because it's light, it likes to move around. And so with this stack that we have, being able to go to high pressure, kind of electrochemically, so we just let the pressure build up in the system, that's a huge benefit as well to reducing these, transportation and logistics costs for that whole delivered cost of hydrogen.
Yeah, I'm coming up with all these hydrogen analogies. So, like, the hydrogen molecule is like herding cats. Like, it just wants to go where
Yeah,
it wants
for
to go.
sure.
So you're. I want to make sure I understand. So you're electrochemically increasing the pressure. So then you don't have to have all these other machines to do that on the back end of the production line.
Exactly. So what would normally happen with an electrolyzer is you would split the hydrogen, the water into hydrogen and oxygen, and the challenge would be at a certain pressure, you would actually get the gases mixing again, even though you have a membrane. And so because the gases would start to mix, that you basically have a max pressure you can get to. So then you take the hydrogen out of the stack and then you use a mechanical compressor. So many of the the electrolyzers today go to about 30 bar, which is nice for a lot of chemical synthesis, but it's not a nice pressure for transporting the hydrogen. So tube trailers are operating more at 200 to 300 bar or 200 to 300 atmospheres. And so with our technology, so because we can manage that hydrogen and oxygen mixing better, we can basically, all we have to do is pressurize the water coming in, and then that hydrogen builds up in the system and it's not going to leak over onto the oxygen side. So that's how we're doing it, basically managing the gases mixing.
And for those that don't understand the need for this high pressure, to me, it seems like it's both. You want to transport as much hydrogen as you want, as you can, so you need it at a higher pressure, but then also a higher pressure helps stabilize it. Is that correct?
Stabilize is an interesting question. I don't know if I'm super knowledgeable on that. What I would say is, if I'm remembering correctly off the top of my head, hydrogen has about one third the volumetric density as natural gas. So if you have this same container and you have the same pressure, you're only going to get one third out of the energy out of it. And so you do want to just go to higher pressures with hydrogen because it's more of it's a light gas. It's not as heavy as natural gas. So that's on the financial side. You may be very right about the containment and kind of the making it more stable, but I'm not as familiar with that.
I don't know if I am or not, so I'll put it in the show notes whether I am or not, and
Sounds good.
people who are interested can go to the show notes. So you're talking about sort of from the finance perspective, wanting to basically pack more molecules into the same space with that pressure. Um, there's this goal of the industry to achieve like $2 a kilogram of hydrogen production, and that's a key benchmark everybody's going for. How do you see the power to hydrogen hybrid electrolyzer helping the whole industry get to that goal?
So the $2 per kilogram is typically a production cost. So we've actually ended up talking a lot about logistics and transportation, so that's not as included. Let's just talk about the production cost for now. So one of the ways we look at the industry is everyone talks about electrolyzers use a lot of electricity, and it's 100% true. Typically 70% of the cost of a kilogram of hydrogen from an electrolyzer is going to be the electricity cost. Now, okay, so let's reduce the electrical use of the electrolyzer. That's a great thought. But what we already have today is electrolyzers. Most of the electrolyzers on the market are probably 80% efficient. So there's room to get better, but we're hitting the top of the ceiling, or we're hitting the ceiling as far as where we're getting on efficiency. So the way that we look at it, much more importantly, we talked about this a little bit early on in the show, is, okay, so if electrolyzers are getting too close to where they're going to get on the efficiency side, how do we look at the problem in a different way? And the way that we look at it is, how can we access the lowest cost electricity? So we've written about this a little bit. If you were to have a free and 100% efficient electrolyzer, so essentially, a unicorn, and you use the average US grid electricity price, which is I think around 9 cents per kilowatt hour. So you've got a free electrolyzer, it's perfectly efficient, but you use the average US electricity price, your hydrogen is going to be about $4 to $4.50 per kilogram. It's a non-starter, right, when we're trying to get down to $2 per kilogram. But if you have an electrolyzer that can use behind the meter electricity, so wind and solar, and handle that variability and not need that steady grid power, you can basically cut your electricity price by 2/3 to 70%. So there's lots of areas in the country where you can get behind the meter wind and solar for 3 to 4 cents per kilowatt hour electricity. So even if you have an average electrolyzer using that price of electricity, that's where you get to that $1.50 to $2 per kilogram hydrogen cost. Now, if you're going to use intermittent electricity, then you really have to think about the capital cost of the electrolyzer, because you're not going to get to run it all day. You're not going to get to run it 90% of the day when you're using wind or solar. And so that's why the capital cost, so reducing the fancy metals that you're using, becomes way more important in that scenario. You either want like a super efficient electrolyzer that's running all day and maybe you can use the more expensive things, or you want the cheapest electrolyzer using the simplest components, but it needs to be able to use that variable wind and solar. And so that's the approach that we're taking to it.
So knowing everything that you do about the hydrogen industry, and if we look out 5 to 10 years from now, what is your prediction in terms of what we can expect? Are we actually going to have, like, I kind of feel like we've been on this hydrogen's about to break through moment, for almost over a decade now. And so I'm curious to hear from you. Are we actually going to get to a place where hydrogen production is and especially green hydrogen is more abundant?
I think there are a few things that I will say on that. So yes, we firmly believe clean hydrogen and green hydrogen is going to be a market in the future. I think some of the key things to look at in this space are, number one, today it can make sense to use green hydrogen or clean hydrogen from electrolysis anytime you have cheap renewable energy and high natural gas prices. So we're in Columbus, Ohio. That's not really the case in Columbus, Ohio. But in parts of the globe where you don't really have natural gas, but you have great wind and solar, like think Spain and Portugal, it can be competitive today. So it's really about the natural resources and the inputs that go into the product. So that's number one. Number two, I would say one of the interesting things that we've seen, and we've seen this story in clean tech before, is that China's been really good at scaling clean technologies, but specifically related to hydrogen. China has a lot of resources, but hydrocarbons and fuels are not one of the big resources that they have. They really want to get away from importing fuels from Russia, the Middle East, and the US. And so they are heavily pushing this electrolysis market because they have really good wind and solar. And if they drive the cost down on electrolyzers, they can make their fuels domestically. You were talking about earlier ammonia and e-fuels and things like that. They can make their fuels domestically with low-cost wind and solar and these electrolyzers. So China's committed to this. And then the third thing I would say is in Europe, you're starting to see a lot of the policy that they've had as far as carrots and sticks, and the sticks starting to come into play. So the EU emissions trading scheme, the penalties are starting to get more significant. You just saw, I think late last week or early this week, the International Maritime Organization finally released their rules on decarbonizing shipping. And there's a lot of movement in that space to use low carbon and zero carbon fuels. So we firmly believe that this is going to be a market. I think the argument is whether, I think the days of thinking hydrogen is going to be the panacea and be 20% of all energy market share, it's probably not going to happen. I think the argument is whether it's going to be 3 to 4% or 10%. And I can't say that anyone knows the answer to that, but I would say 100% is going to be a thing. It just may be more regional than you expect, but that's always been the case with the energy ecosystem. Countries and regions use the natural resources they have. And so when you have good wind and solar, you're going to want to use clean hydrogen from electrolysis.
Fascinating. Thank you so much, Alex, for your time and this information. You've enlightened me significantly on some of more of the science around hydrogen and the industry and the production, the transport of it. So I really appreciate you taking the time to explain all that to us.
Yeah, absolutely. Happy to anytime. It's part of the job to kind of educate what we're seeing in the market.
Well, thank you. We will keep in touch and keep our sensors pointed at you, as it were, if I continue my spaceship analogy to its furthest degree. And thank you, Earthlings, as well, for joining us. We'll see you again on another turn of this beautiful blue-green space flower that we call home. Primary financial and production support for Earthlings 2.0 comes from Technica Communications, an award-winning PR firm amplifying breakthrough technologies of the future. Additional supporters include Greenlane, who is working to build a nationwide network of commercial EV charging infrastructure, Tigo Energy, a solar energy and software solutions provider focusing on commercial, industrial, and residential solar installations, Ampion, who is expanding renewable energy access for communities and Fortune 500 companies everywhere through community solar. 24/7 Solar, a next-generation concentrated solar power solution that's modular and can capture the sun's energy at a higher temperature than conventional CSP and store it in simple ceramic pellets. And the U.S. Biochar Initiative, who is increasing production and use of biochar in North America by developing markets, increasing awareness, and building community. And of course, our heartfelt gratitude goes out to you, our listeners, for your curiosity and dedication and showing up with us every week. Thank you so much. We do this for you. If you have a topic you'd like us to cover, or if you want to participate in our Pay It Forward guest model, please contact me at lisaan@earthlingspodcast.com. And you can search our entire archive on any podcast app as well as YouTube. And you can also go to earthlingspodcast.com and search our website there. Until next time, keep exploring and caring for this beautiful blue-green space flower that we call home.